Yeah, and to finish it off, I'm Charlie Wilson. I'm a researcher at the Tyndall Centre also, but at the University of East Anglia, which is in the east of England. And it's really fascinating. So I hope, listening to each of your mini little bios, I hope that there'll be something in this for all of you, but that's maybe a bit ambitious. But hopefully, at least if there isn't something directly related to what you do in this, there'll be something of interest. So Kerjan earlier was talking with a sort of future-oriented perspective on transitions and thinking about low carbon scenarios. I also work in that area, particularly with scenario modelers at an institute in Austria called the ASA. But what I mainly do, and what this is about, is looking at historical evidence so that what we then kind of think about the future is grounded in what we've observed about the past. And so this is what I'm going to talk about today, with a specific emphasis on energy transitions and how fast they can or can't go, which is clearly of crucial relevance when thinking about global energy challenges. This is all obvious to all of you, that the kind of challenges we face on a global scale with respect to energy are not ones solved through kind of tinkering and incremental change. They require system transformation. And decarbonisation is a critical part of that system transformation. But when you look at energy resource substitutions historically, this will be very well known to many of you here, you see, so this is from pretty much the industrial era, 1850, up to the present. You see these three big revolutions or transitions. One from traditional biomass, that's the green, sorry, I should say that these lines are showing the percent of each energy resource in the total global primary energy mix. So in the industrial era, you see the substitution of traditional biomass for coal, and called the steam revolution. In the 20th century, you see the rise of oil and more later on gas, and the continued substitution of biomass and now coal. And this has been called the end-use revolution because it's this kind of era of modern energy services and this explosion of kind of useful things that we get from the energy system. And then from the late 70s and the oil shocks, you see these substitution dynamics kind of flatline a bit. You see coal pretty much stabilize in terms of primary energy share. You see oil decline a little bit, and you see the rise of nuclear and the continued rise of gas. But this is kind of the era which we're hoping will shape into the low carbon revolution. But you can see kind of historically that if you measure the time period over which these energy resource substitutions take place, and there's a metric that's commonly used in these kinds of studies called the delta T, or the turnover time of these systems, these delta T's are quite long. So there are different definitions of what the time period of an energy transition is, but they all share this view that they're quite long. So, for example, Grubler, a colleague of mine, he describes a transition as meaning a change in the state of an energy system, and he measures it using this delta T value. And so that's from 1 to 50% change in the share of global primary energy. Václav Smil, a very prolific energy historian in Canada, describes an energy transition as the claiming of a substantial market share by a new energy resource or a new prime mover. And he measures this from the first introduction of a resource or a prime mover to 25% market share. And a colleague of mine in the UK, Roger Fouquet, who looks at long-run energy transitions in the UK context, he describes a transition as a switch in the dependency of an economic system from one set or cluster of energy resources and technologies to another. And then he defines energy transitions or measures them in a slightly different way. But in all cases, these energy transitions which we've observed historically have been multi-decadal processes, long processes. So hence the conventional wisdom that energy transitions take time. But earlier this year, a paper came out in a journal called Energy Research and Social Science by Ben Sovacool, who is a professor of energy studies at the University of Sussex and writes prolifically on a whole range of energy issues. And he published this work saying, actually, you can observe very rapid transitions historically, and we can learn from these to shape the kind of future low carbon transitions that we're interested in. And in his paper, he says, here's a whole bunch of evidence that transitions can move very rapidly. So here are 5 end-use transitions, so transitions in essentially end-use technologies and services that Sovacool uses to say things can go quickly. Energy-efficient lighting ballasts in commercial buildings in Sweden, energy efficient cook stoves, improved cook stoves in China, LPG cook stoves in Indonesia, flex fuel vehicles in Brazil, which can burn either ethanol or petrol, and air conditioning, the diffusion of air conditioning in the USA. And so you can see the kind of time periods over which these transitions happened, according to Sovacool, and then using this measure of a 1 to 25% market share, which is what he uses, he shows these transitions have all happened very rapidly, less than 10 years in many cases. And beneath each of these transitions is an underlying study or some underlying studies. This is one, for example, on lighting ballasts in Sweden. So if you look at the line with the white diamonds, this is showing the market share of these energy efficient lighting ballasts in commercial buildings. So from roughly 1% up to 25%, that period is this 7-year period of the transition, according to Sovacool. So these are all end-use transitions, and he does the same for energy supply transitions. So in this case, his examples are the birth or the emergence of the oil industry and the electricity system in Kuwait after World War II, the rapid growth of the gas sector in Holland with the discovery of the Groningen gas field in the 60s, the build-out of nuclear power in France in the 70s, the switch in Denmark from oil-burning boilers to coal and gas-burning CHP plants through the late 70s and early 80s. And an interesting one, this recent one, which is a phase-out of coal power in Ontario, the largest province in Canada, where the government essentially announced a phase-out to take place over 10 years of all their coal-fired power plant. And again, in each of these cases, you can see the measured transition speeds less than or around about 10 or so years. So very, very different from the conventional wisdom that I showed before, where these transitions take, 70, 80 plus years. Has anyone, just out of interest, has anyone read this this argument from Sovacool? Yeah, okay, well, I'd be fascinated to see what you both think. Okay, 3 of you, okay. So what we've done in a response to this is what I should say is that Sovacool, much to his credit, invited a whole bunch of other people who work on energy transitions, including myself, to write responses to his proposition that energy transitions go rapidly. So I think now there's 8 short responses to his original article in the same journal. So this is as close as academics get to kind of throwing mud pies at each other in a very measured way through peer review and 6 months delayed and so on and so on. But basically, there's a big spat in this journal about, can transitions go rapidly or do they go slowly? So what I want to sort of share with you is with Arnulf Grubler, our arguments as to why Sovacool was essentially wrong, that transitions can go very rapidly. And that's because if you look at the characteristics of transitions, he was highly selective in the ones he picked. So I want to share with you 5 key characteristics of historical transitions. And the first is that although the diffusion of discrete innovations or discrete technologies can be quite rapid, particularly if they're a ready substitute for something that's already in the market, change in technological systems, or at a systems level, change is very slow. And that's fundamentally because of interdependencies between technologies, infrastructures, and the kind of institutions or rules or contexts in which those technologies are used. Václav Smil puts this very characteristically succinctly by saying scale matters. And here's a nice empirical example of this. That if you look at, this is all relating to railway, so trains and railways, and the delta T's, remember the turnover time of these various technological changes. And this is both in the USA and the USSR, so you can kind of control, if you like, for these very different changes in institutional environment between Soviet, USSR and the USA. So if you look at an individual technology, diesel engines substituting for steam engines on locomotives, the delta T's were pretty quick. But if you go up to the network level and you look at, say, the treatment of railway ties in the USA or the electrification of railways in the USSR, the delta T's become longer, the turnover time or the transition times become longer. If you then scale up to the level of the whole railway network, with all the engines, all the track, all the stations, all the refueling infrastructure and so on, the delta T's become longer still. And if you then scale up from the railway network to the kind of network of long distance communication, and in the US this particularly meant the evolution of the telegraph, the system of sending telegraphs long distance, as well as people and goods long distance via the railways, then the delta T's become longer still. In other words, as you go up in scale and you increase in complexity and interdependency, your transitions become longer. So when you look then at Sovacool's example, so here are his 5 end-use examples of rapid transitions. They're rapid because, in many cases, he was looking at the diffusion of an individual technology rather than a broader systems transition. In many cases, in many cases where I put a red blob, that's where I think his example is guilty, if you like, of this selective criteria. So many of his transitions were diffusion processes rather than transitions. They were diffusion processes of ready substitute technologies that kind of slotted in to existing infrastructure and practices. They were relatively low in complexity and in scale, and in some cases they were very small market sizes. In other words, all those reasons would lead you to think we expect that these would be rapid for all those reasons. And the same kind of story goes for some of the energy supply transitions that he also looked at. So I won't go through each in detail, but essentially the darker red is where I think this condition of rapid transitions applies quite strongly, and the lighter red is where I think there's some correspondence between these rapid transitions in his case studies. Okay, so the second characteristic of transitions is that formative phases are really important. And what I mean by a formative phase is essentially the period prior to mass market commercialization, during which a new innovation system is being set up to support the subsequent commercial development of a technology. And this, from the whole literature around innovation systems, we know that innovation systems play certain critical functions which then allow successful commercialization. So these formative phases are particularly relevant in the markets where new innovations are first being commercialized. This is the kind of center of all the sort of experimentation and learning and refinement and testing and so on that goes on in order to then successfully commercialize a technology. So with a colleague, we looked at these formative phases for a whole range of energy technologies, and we essentially measured how long these formative phases were, from the point at which you first see a technology being commercialized 2 years in a row. So you know it's just not just a one-off kind of not random, you know it's just not a one-off kind of failure, if you like. But when technologies first get commercialized to the point at which they reach about 2.5% market share. So all the innovators in the sort of early adopting niche have adopted these technologies. And if you measure these formative phases across a wide range of energy technologies, going back to the steam technologies in the industrial era, through bicycle cars, motorcycles, natural gas power, coal power, and so on, all the way down to contemporary technologies like cell phones and energy efficient light bulbs, then you see that the formative phases, so this phase prior to large scale market diffusion, are over 20 years on average. So that's the thick blue bar on each of those plots. Sorry, and I should say the x-axis here is time, and it goes back to 1700 and up to the present. So the thick blue bar is our best estimate of the time period really before you start seeing this technology appear at scale in the market. So in many cases these are very, very long, and the only kind of significant predictor we found of shorter formative phases were for technologies which were ready substitutes. Again, they could kind of slot in to existing infrastructures and practices. So we would expect therefore these long formative phases with new technologies. And in many of Sovacool's cases, the examples that he uses omit these formative phases. And again, my sort of mapping of Sovacool's case studies onto this particular criterion of rapid transitions is, many of his examples are susceptible to this omission of this long time period before the technologies appear at scale on the market. So again, you would expect his evidence to be of rapid transitions. Okay, third characteristic. Diffusion is faster in later adopting markets because essentially the knowledge gained in those early adopting markets, in those formative phases, can spill over through, for example, trade, through foreign direct investment, and so on. So very simplistically, if kind of formative processes of experimentation and learning help reduce the cost and improve the performance of a technology in market A, and that technology is then commercialized worldwide, essentially markets B, C, and D all benefit from that experience in market A. So this is this kind of very well-known process of knowledge spillover, and if this is right, you would expect to see that the turnover times or the transition times in the original core markets are going to be longer than what you see in subsequent rim and periphery markets. So this language of core, rim, periphery describes how technologies diffuse spatially from the initial innovating regions out to subsequent regions. So this is kind of what we'd expect to see if later adopting markets can benefit from early adopter experience. And this is indeed the case. So again, we took a whole set of different energy technologies and we measured the turnover times in the core, which is the darker colour, through to the periphery, which is the lighter colour. And in most, not all cases, but in most cases, you see that, for example, the turnover time or the transition time in the core is longer than it is in the rim, and then longer still than it is in the periphery. In other words, this is sort of consistent with the argument around knowledge spillover from early adopters to later adopters. And if you go back to Sovacool's examples, again, many but not all, of his examples were essentially later adopters of technologies. They could benefit from global knowledge and know-how around these technologies. So, for example, Sweden was not the first country to kind of invest and adopt energy-efficient lighting ballasts, and Kuwait was not the first country to build an electricity system or an oil industry. So they could benefit from others' experience. So again, you'd expect these transitions to be more rapid. Fourth characteristic of transition is that transition speeds are a function of what advantages an innovation or a system of innovations provides to its adopters. And we know this from sort of 40 or 50 years of work on diffusion, I think very nicely summarized in Rogers's work on diffusion of innovations, where certain innovation attributes explain how rapidly diffusion takes place. And the dominant one by far is relative advantage. So this could be profitability to a firm, if the firm is an adopter, or it could be a whole series of different kinds of advantages to an end user like us as individuals or households, if we were an adopter. There are some other attributes of innovations which explain how fast they diffuse, but this is the dominant one. So strong relative advantage to adopters equals faster diffusion. And again, in Sovacool's case, almost all of the diffusion processes that he examines provide immediate and tangible benefits to the adopters of those technologies. And the really kind of obvious ones would be things like improved clean burning cook stoves in China and Indonesia, which provide very direct and very large benefits in terms of health and respiratory, less problems with respiratory illnesses in very smoky domestic environments. So very strong relative advantages of his transitions. The fifth and final characteristic of transitions is that speed is not just a function of the benefits to adopters, but speed is also a function of the adoption environment, so the environment into which these innovations are diffusing. Now this is the same graph that I showed you before, but the eagle-eyed of you may have spotted this cluster of 3 formative phases in the middle, which are all fairly compressed. And these are all directly or indirectly associated with World War II. So fluid catalytic cracking was a cracking process in refineries that displaced thermal cracking, and then jet aircraft and nuclear power all have their roots in this very peculiar kind of institutional context of World War II, in which there was very, very strong coordination between different actors in the innovation system, whether it was government or large companies or tech developers or users. And very clear and consistent expectations about the direction of the transition that was underway. And so this very particular institutional environment supported these very compressed formative phases and then these rapid diffusion processes. Now there are some people who argue that we can see peacetime examples of very strong coordination. What happened in the 70s in France with the nuclear program is a good example. The Danish wind story through the late 70s, 80s and 90s is another example. And what's happening now in Germany is used as another example. Now I think you can debate legitimately whether these are as strong examples of directed, coordinated, policy-driven transitions as these World War II time examples. But nevertheless, in Sovacool's case, we find that many, again, if not all, of his examples of rapid transitions are characterized by a very kind of strong coordination, very strong alignment between different actors involved in the transition process, and a very clear kind of sense of direction backed up by strong policy. And so again, that's another characteristic of a transition which you'd expect to be rapid. So if you put all this together, then all of these different reasons why we would expect transitions to happen very rapidly are largely evident in the select case studies that Sovacool provides us with for rapid historical transitions. These are the end-use examples, and these are the energy supply examples. In other words, if you were to take the characteristics of the transitions that he analyses, you would expect them to be rapid for all those reasons. So the big question then is this useful for thinking about future low carbon transitions? Does this help us work out what to do, the kind of stuff that Gert-Jan was talking about earlier? And our conclusion was this, and I've learned that in Sweden this makes no sense to people, and in fact you guys, I think, talk about this, that when you're trying to compare two things which are really non-comparable, because they don't have a like-for-like comparison, you talk about apples and pears. So in England we talk about apples and oranges. And we argue that this is really an apple and oranges comparison if you're trying to learn from history about what we need to do in future low carbon transitions. The reason being is that if you think about the kind of system challenges facing us with the global energy system, we need transitions which are systemic rather than specific to discrete technologies. We need transitions which have novel concepts, not yet fully commercially scaled, rather than simply market-ready substitutes. We need transitions which also begin in innovator or early adopting markets and then can spill over to later adopting markets. And for me, this is the kind of critical one. The benefits to the adopters of the various low-carbon energy supply and energy end-use technologies which we need have much less clear benefits to adopters than we've observed historically. So historical energy transitions have tended to be driven by energy end users enjoying improved, cheaper, better, cleaner energy services. And in many cases, it's less clear how this characterises the sorts of things we need to do for a low carbon transition. And finally, we see that in fast transitions, we've generally had this very strong kind of coordination and policy alignment, and we see many, in current examples, problems of different innovation actors not being strongly coordinated, and vested interests and so on, also representing kind of a misalignment between the direction of innovation efforts. So for all these reasons, I think this better characterises what we need, and this characterises what we can see from rapid transitions historically, so hence the kind of apples and oranges comparison. And aside from kind of an analytical interest, this is really important in terms of its policy implications, because I think if you argue strongly and present what we think is highly selective evidence that transitions can go very rapidly, you run the risk of creating kind of over-exuberance and hype, which can lead to boom and bust or stop-go policy cycles. And we've seen this a lot, not just with renewables, but also particularly with alternative fuel vehicles and the kind of cycles of hype from originally hydrogen and fuel cells, and then to biofuels, and then kind of back to hydrogen for a while, and now to electric vehicles. That you can create these very ultimately damaging kind of boom-bust cycles in policy support. And you can also, I think, sort of raise expectations around a kind of discourse of feasibility. This is feasible, this is doable, and this kind of moves away from what we need, which, given the magnitude of the problem, is more a sense of emergency, kind of an emergency discourse, and the need for more radical action. So you can risk undermining this. And I think finally, if you kind of strongly support this idea that transitions can be very rapid, you also run the risk of targeting investments and efforts into specific technologies within a portfolio, because these can happen very rapidly, rather than what I think we need, which is a much more kind of diverse and balanced portfolio across a whole range of technologies. So this was our kind of analysis or conclusion based on the evidence that Sovacool presented. And I think I'll stop there, because I feel I've been bombarding you with words. I've got a few